that we started in class, but we started it without any numbers, and so I figured, why not finish this with numbers? And I think this will help us out, and it'll help us with homework. So the idea is that we have a battery here, an ideal battery, and this is its positive plate and its negative plate, and we're going to flip this capacitor switch down to A, and then it's going to allow capacitor 1, C1 to charge. And I'll make this a little longer so you can tell that that's that length. And then after a long time has passed, we're going to take that switch and flip it from A to B, which essentially removes this part of the circuit and just makes it so these two capacitors are connected to each other. And so C1 is going to discharge some as it charges up C2. And I'd like to know, after that point in time, what is Q1 final, so the prime is just after the switch has been flipped to B, Q2 final, and V1 final, and V2 final. And now, a point that I should make that, at least when we're filming this, that our class has struggled with, and that is that our batteries, people keep thinking that batteries and capacitors, not that they're interchangeable, but that when I say, you know, like the charge on the capacitor is charge that came from the battery, then they feel like if charge is a conserved thing, then the battery should lose charge. Okay, well, if we're dealing with a real battery, like a real chemical battery, you're right, that some charge gets lost from that battery, so to speak, as in the amount of charge, or I guess, you know, its anode and its cathode are they're not both reduced, but there's some reduction in the cell potential over time. We're dealing with what we're calling an ideal battery, in the sense that this battery always has a 12-volt difference. So it's kind of like our electric plug-in-the-wall batteries that we use in class. We're saying that that potential stays the same the whole time. Okay, so you don't have to worry about, well, how much charge was left in the battery, and so is this still 12 volts, or where did that charge go? This battery gives away charge and still maintains that same 12-volt difference. Okay, anyway, on to the video. So the first piece is just figuring out how much is on capacitor 1, how much charge is on capacitor 1 when the switch is at A. So for part A, our circuit really just looks like this. There's just a single capacitor connected to a 12-volt battery. And so for that part, the math is pretty straightforward. Gosh, I'm having trouble writing C's. We can just say that the capacitance of a capacitor is equal to the ratio of how much charge it stores versus voltage difference. We know charge, or per voltage difference, we know charge flows onto this capacitor as long as there's a voltage difference between the battery's two sides and that capacitor plate. And so what's going to happen is the charge is going to keep flowing from the battery until this voltage difference equals this voltage difference. So solving for how much charge it's going to be, that's when we've got C1 times that battery voltage. So Q1 at the end of charging capacitor 1 is just going to be 6 farads, which is a huge capacitor, times 12 volts. So we'd have 72 coulombs of charge. And again, that's an enormous amount of charge, but we're just saying this so that the numbers are neat and easy to work out with. I don't feel like doing things with microfarads and picofarads, etc. right now. All right, the second part, these two are actually kind of out of order, but I wanted to make sure that we did part C to verify a concept that we're going to use in part B. So in part B, it asks you to find the final charge on C1 and C2 after we've taken our circuit and flipped it so that it looks like this. So it's really just capacitor 1 and capacitor 2 connected together. Here's point B where that switch is closed. Okay, so what we talked about in class, what we had a lengthy discussion about in class, was this idea that this charge stopped flowing between capacitor 1 and capacitor 2 when they have equal charge or equal voltage. And we deduced that it's because of equal voltage, because charges in any kind of circuit or in any kind of situation, they flow because of differences in voltage. So the example we talked about in class was this idea of, if you're thinking of taking a free charge and putting it between the plates of a capacitor. So you could do that. You could just take a point charge and put it between these plates. Well, the charge is not going to spontaneously move from a place where there's some voltage to a place with equal voltage. It won't spontaneously do that. But it does move from places of higher voltage to lower voltage if it's a positive test charge. Okay? And so charge is going to keep flowing because of a difference in voltage, not because of a difference in the amount of charge in two places. In fact, if you're thinking about like two different kinds of capacitors, okay, so here's a huge capacitor, here's a little tiny capacitor with the same distance between the plates but different plate areas. Well, in these two capacitors, so they have the same distance between their two plates, it's going to take different amounts of charge on those two plates in order to get them up to the same voltage. And that's because, if I think about what voltage really is, it's inseparably related to potential energy, as in you have a greater difference in potential energy between two places if you also have a greater difference in voltage between two places. Well, potential energy between two charges is all about their proximity to each other. And we've talked about this a couple of times too. Like if you have a plus Q, a big source charge, where would a small test charge have more potential energy? If that small test charge is at A, or if that small test charge is at B. And you guys have all said many times over, well, it's got more potential energy here because it can be pushed farther, or because I've taken two charges and pushed them closer together. Well, the same thing's true when you take those charges and now you put them in a device, like a capacitor, when you're starting to pack charges onto the plates of a capacitor. If you pack the same two positive charges here and here, this is at a much higher voltage because these two charges are packed together much more closely. Or this voltage gap is a much smaller voltage gap than this is because, again, these charges, it's taken a lot more energy to get them this close together. So this would be at a much higher voltage than this, even though there's equal amounts of excess charge on those plates. Okay, so to get up to the same voltage, you'd have to pack a huge amount more charge on this larger capacitor to get it to have the same voltage difference as this does. Well, what that means is with our two capacitors here, not just because they have different capacitances, but in this case it's clearer because they have two capacitances, charge is going to move until they're at the same voltage difference, not until they have the same charge on each capacitor plate. Okay. Alright, with all that said, let's go ahead and solve this problem. So I'll erase all these pictures. Maybe I should have gone with a bigger eraser, but you can always sit at home and think, man, I wonder what he's going to erase next. Oh gosh, this is pretty exciting. Bet he doesn't go over there, but he did. Look at that. Very exciting. You can tell who's tired today. Alright, so let's solve this part. If we want to know then what charge is on each of these two capacitor plates these two capacitors, capacitor 1 and capacitor 2 at the end, we've got to actually begin not from saying Q1 prime equals Q2 prime, but the final voltage on capacitor 1 has to equal the final voltage on capacitor 2. How do you find those capacitances? Well, again, we're going back to our definitions. I said capacitances, I meant voltages. How do you find those two? Go back to the definition of capacitance, where capacitance is also always the ratio of charge to voltage. So that means that voltage is going to equal Q over C. So in our case, this is Q1 prime over C1, and this is Q2 prime over C2. Now from here, there are two different paths you can take. There's the conceptual path, and then there's the, look, I'm just going to grind this out with algebra path. Okay. The conceptual path says, let's do a little manipulation. If I put Q1 prime over Q2 prime, so I just kind of divided by Q2 prime, and if I multiply by C1, I get that the ratio of capacitance 1 to capacitance 2 has to equal the ratio of Q1 prime to Q2 prime. So that actually makes things pretty straightforward, because on the concept side, if C1 is 6 farads and C2 is 12 farads, that's a 1 to 2 ratio. So the same thing should be true about charges. There should be a 1 to 2 ratio of Q1 prime to Q2 prime. Well, my total charge is 72 coulombs. I'm just going to take that and cut it into 3 equal pieces, because when I do that, then this capacitor, C2, gets 2 of those pieces, and capacitor 1 gets 1 of those pieces. So my final charges seem like they should be 24 coulombs and 48 coulombs, which maintain that 2 to 1 ratio or 1 to 2 ratio, and they add up to the total charge that's on that capacitor when C1 is fully charged, and that's the charge that needs to distribute itself between C1 and C2. The thing to remember with that is that charge is conserved in this kind of circuit, because with the capacitor it doesn't have anywhere to go. So if this starts off with 72 coulombs, it's going to send charge over to C2, to capacitor 2, until these two get to be the same voltage. Since this is a lower capacitance, it takes less charge on that capacitor for it to get to the same voltage as capacitor 2 is going to be at. Alright, so that's the rough and ready kind of algebraic method. There's also the brute force algebraic method. I may have called this algebraic. That's conceptual. That's the kind of rough and ready conceptual method, which is the way to go if you can see it, but it's not always that easy to see. Let's say you have to go through this and do it algebraically. Well, then there's a missing piece in this, and that is the relationship that Q1 prime plus Q2 prime has to equal the total charge, which was all the charge that was on capacitor 1 after it was fully charged. if I take that piece of information and I plug it in here, okay, what I could say is that, well, then Q1 prime is equal to Q1 minus Q2 prime. So wherever I see a Q1 prime here, I'm just going to say, oh, well, Q1 prime is equal to Q1 minus Q2 prime over C1, and that has to equal Q2 prime over C2. And then I would just cross multiply and divide and solve for Q2 prime, see what it is, and then take that Q2 prime, plug it back in here, and know that Q2 prime plus Q1 prime gives me Q1, so I could solve for Q1. I've done this. I didn't leave myself enough space for it, but I know that you do get these same two answers. Okay, so that's the algebraic brute force method, is just make that substitution knowing that Q1 prime plus Q2 prime equals Q1. All right, well then we want to take a look at what happens with the voltage, and this is the other really key learning step out of this. So V1 prime, or V1 anywhere, is just the ratio of Q to C. So V1 prime would equal Q1 prime over C1. So V1 prime would equal, let's squeeze this out of the way, scoot this over. V1 prime would equal Q1 prime, which was 24 coulombs, over C1, which was, I think, 6 farads. So that's only 4 volts. V2 prime would equal C2 prime over, or sorry, what am I doing? Q2 prime over C2, which is 48 coulombs over 12 farads. V2 prime also comes out to be 4 volts. A lot of us wanted to jump in and say that these two voltages should be 6 volts and 6 volts, because we said, well, it started at 12 volts. Voltage is conserved, is what we were thinking, so we thought it should end with 6 and 6. That's not the case, through that whole explanation of voltage being about how tightly packed charges are. As you can see, V2 prime is only 4 volts. V1 prime is only 4 volts. If we look at conservation of energy, we may have lost energy in this process of shifting charges around, using that potential energy is 1/2 CV squared. Because as we shift around those charges, they're not packed in the same way, so we don't have things at the same voltage. Okay, so you can check that. That's really kind of the next wrinkle for a problem like this, is how much energy was gained or lost in this process, which we'll talk about tomorrow. But I thought this was hopefully enough to get us through at least tonight's homework. So good luck, and let me know if you need more help.